Welcome to Strength of Material Lectures by Civil Thinking, and today we are going to solve another problem on axially loaded members. Now as you can see on the screen, you have an axially loaded member. Why it is an axially loaded member? You see this is a cantilever, okay? You see this is a cantilever, and when you draw the free body diagram of this cantilever, it is like this. The load is acting downwards, right? Now of course the support here will be an upward reaction like here, but here is also fixed, right? It is fixed. Now when you apply this downward force, here will be a reaction. So here is going to be another reaction. Now coming to the question, we have to determine the stress in the thyroid. Okay, now this, let me call this as A, B and C. You can see BC, it is a cantilever, right? This is a cantilever, and AB, it is a rod. Okay, it's fixed here. We call AB as tie rod, okay, because it ties the cantilever, the free end of the cantilever to A point, right? Because BC is a cantilever, B is the free end of the cantilever, and it ties the free end to this fixed support, right? That's why AB, this vertical rod, is tie rod. Now we have to find the stress in thyroid. Now we know stress, let me call the stress sigma. Stress is load divided by cross sectional area, okay? Now we have to find these two things. In AB, if there is a reaction here, okay, let me call the reaction here as RB, because the reaction at C, it is like this, reaction at C. Here will be another reaction at B, right? And reaction at B will pass through this AB as the axial load, okay? This reaction of the cantilever, this is the reaction of the cantilever, but this reaction of cantilever is also the axial load for this tie, okay? This is the reaction of the cantilever, but it is also the axial force, okay, because it's passing through the axis, okay. Let us assume the cross sectional area of this is AV, okay, cross sectional area, V for vertical, okay. Now it is AB member, right? Now let me call the length of this tie as LV, length of vertical member, which is 0.8 meter. Now I have to find the stress in the tie rod, right? Let sigma be the stress in the tie rod. Then sigma is load divided by area. Load is this RB, so I can write RB divided by AV. AV is the cross sectional area of this. Now as you can see here, we don't know the RB, we also don't know the AV. So let's find these things one by one, okay? So first of all, let me draw the free body diagram of this cantilever, okay? Let me say this is the cantilever, this is B and this is C, okay? This is the free body diagram, and you have a load acting here. This is a UDL load, right? As you can see here, it is 4.4 kilonewton. Let me call this as W. It is 4.4 kilo. Kilo is 10 power 3 Newton per meter, okay? Now here is a reaction. It is RB. This reaction is RC, okay? Now as you can see this, it is a symmetric, right? This is a symmetric beam. So we know in a symmetric beam the reactions are equal and half of the total load. It means reaction at B is equal to reaction at C, okay? They are equal, both the reactions, and they are half of total load. How much is the total load? Now see, it is Newton per meter, right? W is 4.4 10 power 3 Newton per meter, okay? What is the total length is 1.2 meter. So what is the total load? Total load is per meter load multiplied by total length, right? It is WL, okay? Let me call this as L, right? L is 1.2 and W is this. So how much is it? 1 half of 4.4 multiplied by 10 power 3 multiplied by L. L is 1.2. So how much is it? It is 2640 Newton. Okay, so I found reaction at B 2640 Newton, and this is also 2640 Newton. Okay, so we found one variable here. It is 2640 Newton. Okay, now to find the stress we need AV, cross-sectional area of this tie. So how are we going to find the cross-sectional area? Let me erase this first. After that I will show you. You see, when there is a load applied on this cantilever, okay, it is like this. It is a cantilever, right? This is C and this is B. Now when you apply the load here, right, here is a acting a load W, which is like this, right? It is W per unit length per meter, W per meter, because remember I told this is, let it be W. Okay, now due to this load, as you might have known, there will be a deflection in this. Okay, let me change the color. There will be a deflection in this, like this. Okay, now let me call this as B dash. This beam will bend into something like this. All right, now at B the tie rod is connected, right? The tie rod is connected here, right? This is the tie rod is connected like this, right? Now when the B has bent like this BC beam has bent to B dash C, right? There will be an extension in the tie rod, right? Let me call this as delta B. Okay, delta B is the elongation of AB member, and delta B is also the deflection of B. Now delta B, when we consider it to be elongation of the member, we know elongation of the member is PL upon AE. Okay, now when I draw the free body diagram of this tie member, right, here is a reaction RB. Okay, it is going to be like this, right? Now the length is LV. Let me call the length of tie member as LV, right? And the elongation is delta B, right? Let me call this as elongation. From here to here it is delta B. And the delta B is load, axial load, which is RB. Look at the diagram. Look at this diagram. Axial load, this delta B is equal to axial load multiplied by length LV upon cross-sectional area. Okay, remember I told you cross-sectional area is AV, and multiplied by Young's modulus of this member. Okay, E, right? Now this is the elongation of this member, this tie member, but this elongation is also equal to the deflection, as it is very clear from this diagram. Delta B, if you look at BC, the bend, it truly seems the deflection of B, right? But when you consider this A B B dash, forget this, only see A B B dash, it is the elongation of B to B dash, right? Now so delta B is what? It is the elongation of AB, and also it is the deflection of BC. Now BC, it is what? It is a cantilever loaded with W, W UDL, right? W per unit length, right? Let L be the length. Now it will deflect like something like this, right? This deflection at the free end is delta V, right? As you can see here, it is delta V. Now delta B is WL4 divided by 8EI. Okay, so this delta B is because the so this okay, so it is delta B is equal to this. It is also equal to WL4 divided by 8 EI, right? Because delta B is the elongation of the tie and delta B is also the deflection of cantilever, right? RB, we found the R reaction at B, it is 2640 Newton. 2640 Newton. Now LV is the length of the vertical, it is 0.8, right? AV, we don't know. E, now here is E and here is E, they will cancel out, right? Now W, it is what? W is 4.4 kilo. Kilo means 10 to power 3, right? It is 4.4 multiplied by 10 power 3 multiplied by L4, right? Now L is what? L is 1.2. 1.2 power 4, right? Now 8I. I is what? I is the moment of inertia. I for the cantilever is 24 multiplied by 10 to power minus 6, okay? So I will write here 24 multiplied by 10 to power minus 6 meter 4, okay? Now you have this equation, okay? Now you can clearly see, you can find the value of AV from here, right? Because everything is given, just the AV is unknown. So when I use the calculator, you will get AV to be. So from here we found AV to be 4.44 multiplied by 10 to power minus 5 meter square, okay? Now we also found AV, okay? So here we found AV to be 4.4 multiplied by 10 to power minus 5 meter square, right? Now we have both the terms, numerator and denominator, so we can easily find the stress, right? So let me use the calculator. We found sigma to be 60,000,000. This is Newton and this is meter square, okay? Newton per meter square, okay? Now when you convert it into mega, it is going to be, this is 3 zeros and these are 3 zeros, it is going to be 60 mega. Now Newton per meter square is also Pascal, right? Pascal, this is 60 mega Pascal, okay? Now we have solved this problem and we have finally found the stress in this tie rod AB in this axially loaded member, okay? Stress in the AB, it is approximately 60 mega Pascal, right? Now that is it, we've solved this problem. Now if you have any problem in understanding, please comment. Also, if you need help in solving a strength of material problem or engineering mechanics problem or mechanics of materials numerical problem or conceptual problem in strength of materials, you can contact me. The link to contact me is in the description. You can contact me and I will definitely help you. And that's it for today. See you in the next class. Take care.